Thank you very much, Thomas, for the introduction, and thank you for the invitation. So my name is Rajiv Krishnakumar, and I'm a quantum algorithms researcher at QuantumBasel. So QuantumBasel is a company that was founded 2 years ago now, and we are over at Arlesheim, the Uptown Basel campus. So I'm here today to talk about, bringing quantum computing from the lab to industry, but really I'm going to use it as an excuse to talk about quantum computing a bit in general. So after briefly introducing quantum technologies, I will talk a little bit about where we are with quantum computing. There will be a little bit of overlap with what Marco said, which is a good thing because I think it means we agree on many factors. But then a little bit of what to do now that it's here, or what are we trying to do with it. And then finally at the end, maybe hopefully we'll have some time to, at a high level, at least start unpacking this black box that is a quantum computer so that there's a sense of why we think it can be an interesting technology. Okay, so we'll start with quantum technologies in general. So when someone says they're working in the field of quantum technologies, they are working on either building or trying to find a use for a machine or a box, right? And this box can do one of three things. It can compute some sort of computation that you'd like to do, like solve some mathematical problem. It can communicate, so it can send and receive information, or it can do some sensing. Therefore, it can measure some sort of physical quantity. And Mathieu will talk more about the sensing part in his talk. So I'll leave that to him. And we've heard a little bit about communication in general, and we will talk, now more about the quantum computing side. So where are we with quantum computers today? So kind of the idea is that quantum computers have been around for a little bit, as Marco mentioned, but they're relatively new compared to the regular computers we have, right? And the idea is that we are at a stage where we're trying to really understand how to make them useful. And we're bringing it to a point where, some point in the near/medium future, depending on who you ask, they will become useful for a real industry setting. Right now, we're doing things like proof of concepts with them, and really trying to make that even better. But they will be useful at some point in the near future. And I think another thing I like to talk about is I don't think they're like iPhones. By what I mean by that is an iPhone came out maybe 2007. And then, 4 or 5 years later, everybody had a smartphone, and we were throwing away all the old phones, right? As Marco mentioned, the quantum computing is a computer that will be used in conjunction with regular computing, and also for specific problems. And not only that, but I think what will happen is we will kind of find and be able to implement it for maybe one specific problem at some point, soonish. And then, a year later we'll find another specific problem, and a year later another one, and it'll kind of pop up in that regard, and it won't be like a general sweep of, hey, we have quantum computers, and they're this powerful, in 2 years, and therefore we can use them for everything. So that's kind of the takeaway I wanted to give with this slide. But okay, what types of uses? I keep saying, well, we want to use them for specific use cases. What kind of use cases do we think they can be interesting for? And on the slide on the left, you have some mathematical versions of the problems we think we can solve. Right? Cryptography is maybe not a problem to solve, but a problem-causing situation. But the other ones of simulation, optimization, artificial intelligence, differential equations, we have some ideas on how quantum computers, we know quantum computers can help solve this problem. And on the right-hand side, you have the different verticals that use these types of mathematical formulations. And this is across industry. Now, I said we know that quantum computers can solve these problems, but that's not the interesting question, right? The interesting question is really, how can we eventually do better with the addition of quantum computers than we can if we don't have quantum computers? And this is where, we are really trying to answer and build up the industry to answer this question, right? So what do you do to try and solve this problem of how to use quantum computers in a way that's more efficient than using today's computers? Well, you either work on building computers, or you work on figuring out how to use these computers once they're being built. Because as I will mention a little bit later, it's a very different style of computing than the regular computers today. It's not just, as Marco said, it's not the same thing but faster, but it's a totally different way of thinking. So okay, these are big things to work on, and in fact it requires, these are just a handful of examples of the different types of subfields within these two big questions to work on to try and really make quantum computers useful. So there is, I'm going to start a little bit with the left one in terms of building the computer. We at QuantumBasel, we don't build the computers, and I'm not a specialist in that, but I thought I would still give it a peek. So you saw Marco showed the IBM one system. If you open that up a little bit on the top right, it looks something like the one on the top right. It's not exactly the same one. But if you look at the bottom one, it's a picture of a different type of technology used to also make a quantum computer. And on the left, you have all the type of different possible building blocks of quantum computers, or I guess in this case, quantum bits. And I think the takeaway of this is that we're still at a fairly early stage where there are different ideas as to how to build the best quantum computer, i.e. one that scales well and that can reduce in noise. And all of these have pros and cons. There's no clear, I guess, winner as of now. And in the future, it may be, one of these. It may be one that is not even shown up yet. It may be a combination. We're not entirely sure, but we are making really good progress in that area. So, okay, so I've talked about, building quantum computers. I will talk a little bit about finding out how to use them. But what is coming out of all this? In addition to the actual devices being built, you also have many research papers and patents coming up, right? And I think we're kind of in an interesting place to talk about quantum, because we're not too late, right, to start to try and think about, even as an end user, how to use quantum, because we're still at an early stage. But I think we're not too early either. One, because as mentioned, we have these physical machines that we can access through the cloud, and so we can start using them. But two, we also have companies, it's come to the industry for companies to think about how to make quantum useful. And what I mean by that is, if you would want to start to understand that, you don't have to hire your own team of scientists to do that. There are other companies out there, like us, that can help you along with that journey. So I think we're kind of at a really interesting stage to understand that. And our motivation is, again, going back to the idea that the use cases will be very specific. So I'm very excited to try and find out really where those use cases are, and it can only really be done, in my opinion, eventually, with the help of companies. I think we can sit in our, in our labs, especially us theory people, and kind of think of problems that may be interesting, but it's much more interesting to talk to companies or people that want to use them for solving their use cases. Okay, and it's happening, in Switzerland as well. There's this kind of a nice map of some of the things that are happening around the quantum ecosystem. I just wanted to point this out to say, in Basel there are quite a few as well. So we have things going on, and more information. This is from the SwissNext website, so definitely feel free to check it out. But it's kind of encouraging to see this. Maybe one other thing I'll say is, it's kind of at a nice collaborative stage, where really we are able to share what we found so far, right? Because nobody has a device powerful enough to solve everybody's use cases. So I think it's a really nice moment in the community where we can really share a lot of our results to try and all move forward. Okay, so as I mentioned, we at QuantumBasel, we're working on trying to understand how to bring quantum from the lab to the industry. And we work more on the application side, so more on the kind of algorithm side, the theory side, but that's not the only thing that it takes to bring quantum to the industry. So we partner with people. That's how we like to work. And I want to talk a little bit about the partners on the left, so the technology partners. You see notably IBM, D-Wave, and IonQ. And these are some of the companies out there building quantum machines. And we have access to, well, we have access to their systems over the cloud, which is great. And more importantly, we also have a collaborative spirit with the staff, with the scientists working there. And I want to talk very briefly about maybe IonQ a little bit. So this is, as Thomas mentioned, they're the company that are building a physical quantum computer in Arlesheim. So that's being built, well, in the same building that we are. We're on the 4th floor. They're building it on the ground floor. It should be, it's in the final stages, and it'll be operational in I think January, if not sometime in Q1 of 2025. So we're pretty excited about that, to have a computer on site as well, to try and understand what kind of additional potential that could bring to our collaborations. And of course, we have to partner with academic partners and even accelerators, venture capitalism. We're really trying to bring the ecosystem together, as they say. And what do we do with all this partnership? Well, eventually we want to work with some companies to try and exactly answer this question as to how it can be useful for these real world problems. And I'm happy to talk about some of these a little bit more in detail during the apéro, but maybe the main takeaway messages is that we're very happy to be working with customers. And ultimately, from this, what do we get today? Really, the deliverables are, I would say, just 3 things. It's, well, with the 4th one. So the 3 real things we deliver is a piece of code, or a research paper, or a patent, or some combination, right? And of course, the 4th thing I would argue maybe is the most important one. It's kind of the knowledge transfer. So a company might be interested. I mean, a patent is pretty clear what the value is. You can have it, and then when the computers become big enough, you can use that same algorithm or modify it a little bit for your use cases. But even the research and the code is useful internally, so that as and when the hardware develops even more, the people inside the company already have an idea of what this system is, how to use it, how to start implementing it, so they can really hit the ground running. So that's kind of what we do. That's our main bread and butter at QuantumBasel. Maybe one more thing to add is, so this is the sort of projects that I've highlighted, this way of working with companies. A few other things I want to add. We have innovation-specific, industry-specific innovation events, essentially. So this is another activity we do. We can invite, for example, we had not so long ago, our logistics superposition event, we called it, where we came along with our partners. So IBM was there, IonQ and D-Wave were also there, and we invited people from companies that were in the field of logistics to really have a roundtable and understand where we can take things forward. So that's one of the other things we do. A couple of other ones, so for companies that are maybe a little bit timid and say, okay, we don't want to just dive into a project straight away. Let's have a training session, whether it's for the C-suite, so to give a bigger picture, or to do more trainings for data scientists. And finally, the last thing we do is direct technology access. This is not our main business, but we say, okay, if you're a startup and you want to access different types of quantum computers, because let's say you're a quantum startup, maybe it's a bit expensive to go to each vendor individually. You can come to us and we can make a kind of deal. Okay, that was the sales pitch part of my talk. And maybe I can go now in the last few minutes to talk a little bit about this quantum computer as a box and open it a little bit. Right? So why do we think quantum computers will be more powerful? Really, it's this idea that you see here that you may have heard of, this idea of calculating things simultaneously or putting things in superposition. So I'll let this animation play, and the idea is that that the building block of a quantum computer is a quantum bit or a qubit, and it can be in the so-called superposition state, which is both a 1 and a 0 at the same time. And so with very few quantum bits, you can be in a superposition of many, many states, right? It's actually kind of exponentially large. And so the idea is that if you have, quote unquote, a few qubits, you can bring so many states into the picture that you can start doing like many calculations simultaneously and potentially have an exponential increase in your compute power, right? And so maybe I'll just want to bring this more to a like problems perspective rather than a quantum bits perspective. And what does that mean? So it means, let's say you have a problem and you want to solve it. You can explore all your solutions at the same time, and you say, okay, some solutions are impossible, some solutions are inefficient, but it's okay, because if I'm exploring at least many, many solutions all at the same time, I can find the best one in it. Okay, so if I stop my explanation now, this seems like a magic bullet, right? I've just said, oh, it's a computer, and it can do calculations simultaneously, and you can look at all your solutions at the same time, and right now, I sort of sold a dream, right? But there's a crucial element in this, right? And the crucial element is the way you use a quantum computer is in 2 steps. And I've just explained the first step, where I've said you look at all the solutions at the same time. And the reason is because a quantum computer is a random machine, right? And it's not random because we're bad at building them. It's random because quantum mechanics intrinsically is random. So why am I saying all this? Well, actually what it means is when you look at all the solutions at the same time, right, you're actually not looking at it. It's in the computer, but when you ask for a solution from it, you say, look, explore all the possibilities and give me a solution. It'll give you one of these solutions actually at random. And by default, it'll kind of give you the probability of getting a solution is equally viable. And of course, if you're trying to solve a problem, you're just saying, give me all the solutions. I mean, most of them are not going to be the one you're looking for. They're either going to be, impossible if it's let's say it's a problem of like, hey, I want to, one of the examples we had was working on connecting all the HVAC tubes, right? If you want to find the most efficient method you have like 4 rooms, you want to connect the tubes, and there are many constraints. Well, most of the answers are going to be like, well, take a tube and go up and back down through the ceiling, and you're like, well, we can't do that, right? And some are going to be correct but very inefficient, but really the best combination is going to be very few of them. So now, what can you do? If this is where you're at, where when you ask for a solution, it gives you a random one, well, you can ask the computer to explore all the solutions, ask for one, and it'll give you a random one, and if it's not a good one, well, you can keep doing that again and again. This again defeats the purpose, because you might as well use a regular computer to just randomly look at different solutions. So what you have to do though, and that's the second step of your solution, is you have to somehow increase the probability of it to give you the efficient solution that you're looking for. And this is where kind of the devil's in the detail, because the step from the step 2 is very use case specific. So now this is why, it kind of ties back to the reason that, okay, it's not going to be like an iPhone where all of a sudden you have one solution fits all, because this step is kind of, yes, algorithmically there's a few differences between use cases, but it's sort of generic, right? You can do this for many use cases. But getting from here to here is very use case specific. And in fact, not only is the actual algorithm use case specific, but how efficient that algorithm is also very use case specific. So you'll get some situations, for example, this cryptography breaking one, where, well, that step is, algorithmically very efficient, and so it can do this much, much faster than a regular computer. But there are other situations where you'll find, well, actually, no, it's just as fast as a regular computer, and therefore you might as well use the regular computer because you have that whole system set up already, and there's everything in between. Right, so really, I think that's the message I want to get across in this opening this black box a little bit, is it does things in parallel, but you have to be very, well, clever, but also happen to have a solution that's very efficient for the problem you are looking for. And again, there are situations where we know that there aren't one, there are situations we know that there is one, and then there's sort of this big chasm in between, which we're excited to continue exploring. Okay, so with that, I just want to also, give a shout out to the whole company. This is everybody in the company, so we're a small company, but we're growing. And also, thank you for listening to my presentation.
Thank you. Thank you very much. We'll be back later for